This is section 10.8 of Honors Algebra 2, E, and the natural log. Recall the formula for compound interest that we had in the last video and used in the last class. A equals P times 1 plus R over N to the NT power, where R is the annual interest rate, N is the number of times in the year that your money is compounded, and T is the amount of time, and P is the amount of money you start with. Remember, the way compound interest works is you are earning interest on your interest. So if your money is compounded monthly at the end of the first month, you earn the interest on the money you have in your account at the end of the first month. But you are then granted your interest from that first month. It stays in your account. You are earning interest in the second month then on the amount of money you had in the first month and the interest that was added at the end of the first month. So you're earning interest on your interest. So let's consider the case where T is 1 year and R is 100%. And let's start with P being $1. So you've got $1. You've got A equals 1 plus 1 over N to the N power. Because R is 1, T is 1, P is 1. So in other words, I want to look just at the role of N. How does the number of times that compounding occurs in the year affect the amount in the account at the end of the year? So how much more money do I get if my money is compounded weekly instead of monthly? Or how much more money do I get if my money is compounded daily instead of weekly? In other words, if my money is compounded more and more often, could my money grow at a faster and faster rate? Well, let's investigate. Here's a table that gives you different values for N: 12, 52, 365, 730, 10,000, 100,000, and the values of 1 plus 1 over N to the N power. So if it's compounded monthly, there are 12 months in the year, I would have 2.6130353. I'd have $2.61 instead of $1 at the end of the year. Because I started with $1, remember. If it's compounded weekly, so there are 52 weeks in a year, at the end of the year I'd have $2.69, 2.692597. Let's say it's compounded daily. At the end of the year I'd only have $2.71, 2.7145675. Compounding daily and compounding monthly is a significant difference in N, but it doesn't lead to that much of a difference in the amount of money I have. 10 cents between compounding monthly and compounding daily. So I make more money, but not a whole lot more. Let's say I compounded twice a day, so 730 times in a typical year. I'd still only make $2.72 now if I round it up. 2.7164223. Let's say it's compounded 10,000 times in 1 year. I'd only have $2.72 again by rounding up, 2.7181459. Let's say it's even compounded 100,000 times in a given year. Notice the small difference that occurs in the amount of money I have between 10,000 times in a year and 100,000 times in a year, 2.7182682. I have to go all the way out to the fourth decimal point to notice a difference. So that's a huge difference in the number of times it's being compounded in a year, but the very, very small difference in the amount of money I'm making, the amount of interest I'm earning. So let's say, theoretically, I could compound my money an infinite number of times in a given year. How much would I have at the end of the year? That's the number E. E is that limiting value that 1 plus 1 over N to the N power is approaching as N gets larger and larger and larger. So if I look at a graph of 1 plus 1 over N to the N power, it levels off as N gets larger and larger. It approaches a certain value, an asymptote, you might say. And that value that it's approaching is the number E. And E is approximately the number 2.7182828459045 ... It never ends, never repeats. It's an irrational number. So this quantity, 1 plus 1 over N to the N power, is going to approach a certain value. It's never going to go higher than E. Even if N is infinitely large, it will just be E. So that's the way we define the number E. The number E is said to be the limit, as N goes to infinity, of 1 plus 1 over n to the n power. So limit just means that limiting value. What am I approaching as n gets larger and larger and larger and larger? So e is an irrational and transcendental number, just like pi. So irrational means it cannot be written as a fraction of two integers. Its decimal expansion continues on forever, never ends, never repeats. Transcendental means that it is not the root of any polynomial with rational coefficients. So pi is not the root of any polynomial with rational coefficients, neither is e. Now that could not be said for, say, the square root of 2. The square root of 2 is the root of x squared minus 2 equals 0. A transcendental number is not the root of any polynomial with rational coefficients. When e is the base of a logarithm, we call that logarithm the natural logarithm. And we write it as ln for natural log. So the log base e of x is really the ln of x. Just different notation to represent a log with a base of e. So if f of x equals the ln of x, what is the inverse of the ln of x? Well, remember the way this works. The inverse is going to be e to the x power. So that's an exponential function with a base of e. So here are the graphs of y equals ln of x and y equals e to the x. The ln of x is the blue one here, and e to the x is the red one. So they are inverses of each other. Notice they are symmetric about the line y equals x. They're reflections of each other over that line. Notice e to the x goes to the point 0, 1, as our exponential functions always do, because if x is 0, we'd have e to the 0 power, which is 1. And similarly, the graph ln of x goes to the point 1, 0. The ln of 1 is 0. So these are just an exponential function and its equivalent logarithmic inverse. Here's some examples. Simplify ln of 1 over e squared. Well, 1 over e squared I could rewrite as e to the negative 2 power. So this is the ln of e to the negative 2. I can bring the exponent out front and have negative 2 times the ln of e. Right? The ln has a base of e, so this is really negative 2 times the log base e of e. What's the log base e of e? That's 1. It's just negative 2 times 1, which is negative 2. Let's condense 2 ln of 5 plus ln of 4 minus 3. All right, the 2 we can bring in front, or bring inside, as a power of 5. So the ln of 5 squared plus the ln of 4 minus, now 3, I want to be able to write that as an ln so that I can combine it. It's really 3 times the ln of e. The ln of e is 1 because it's a log base e of e. So this is really the ln of 5 squared plus the ln of 4. Well, when two logs have the same base and they're added, we can combine them as one log we're multiplying inside. So this is really the ln of 25 times 4 minus, I can bring that 3 inside here as the ln of e cubed. Okay, 25 times 4 is 100. And I've got two logs that are being subtracted with the same base. I can combine them as one log in which I am dividing on the inside. The ln of 100 over e cubed. So I've condensed it down to one simplified logarithm. Solve. The ln of 1 over x equals 2. Let's take that logarithmic equation, rewrite it as its equivalent exponential equation. That would mean that 1 over x equal log is e, so that becomes the base of the exponent, and 2 becomes the new exponent. 1 over x equals e squared. That's the same as saying 1 equals x times e squared, or x equals 1 over e squared. I can leave my answer like that because e is a number, so that's a simplified fraction. Number 4, solve e to the 2x equals 9. Let's take that exponential equation, rewrite it as its equivalent logarithmic equation, because that's the only way that I can solve for the variable that's in the exponent. The logarithmic equation would say 2x, the exponent, equals the log with a base of e, so that's the ln of 9. And then I solve this for x by dividing both sides by 2. So x equals ln of 9 over 2, or 1/2 times the ln of 9. 1/2 I can bring inside Make this the ln of 9 to the 1/2 power. Well, the 1/2 power is really the square root, so this is the ln of the square root of 9, which is the ln of 3. Here are your immediate practice problems. Number 1, simplify the ln of 1. That's log base e of 1. Number 2, condense the ln of 5 minus the ln of 4 plus the ln of 12. Number 3, solve e to the 3x equals 27. That is the end of section 10.8.